What is the future of CMOS imaging and focusing on scientific imaging and medical imaging rather than the consumer markets? So I think the advances that we're going to see, one, I mean, of course, greater use of thin devices, two-sided processing. We need to use probably different primary detection material. I mean, at the moment, I think we use a lot of things like cesium iodide, etc. But there are some new sensing materials coming along. We're always after materials which have higher efficiency and higher speed. So we will be using CMOS readout in a hybrid fashion with layers on front of it for primary detection. We also, I think, there's been a great push traditionally on the, if you like, the life science, the wet chemistry side for working in the ultraviolet. That seems to be changing, and now the interest is in the near infrared. So we need to expand how we can make CMOS sensors work probably in the near infrared. The far infrared, I don't think is of much use for these sort of applications. So anything over about 1,000 angstrom, so we've got to have something in front of it. We also always want lower and lower noise. We're getting pretty good on that, actually. I mean, CMOS competes pretty well with the traditional baseline of CCDs, and speed. Speed is always important because the bottleneck is getting the data out, and also radiation hardness is important for lots of extreme environments, not just in medicine but in lots of sciences and of course space as well. And these fully depleted CMOS, which are progressing, I mean, they're a fairly advanced state at the moment, they're not particularly commercial. I think that will grow. I think also, we're living in the age of AI. It's everywhere. And we will involve more intelligence on the chip. Not probably in the primary detecting plane, but we will use 3D stacking. We will have wafers stacked on top of the other, and a lot more processing will occur. We have to have intelligent imaging. The data rates are still phenomenal. My current system, I can manage to track nearly 1 billion protons per second, which is pretty fast. But people want to go faster. I mean, if I go back to my system, then I have to turn down the beam current in the generator, the cyclotron that generates protons, from its treatment levels to something maybe 1,000 times less. And one wants ideally to do it at those treatment levels, but the numbers, the number of protons, the speed you've got to work is just out of reach at the moment. So we do have to put intelligence at the front end, and really, I suppose, to work more like our own human vision. If you look at our eyes, we have about 6 million cones for color vision, fine detail, about 100 million rods around the periphery, and the bandwidth of the optic nerve that gets the information into our brain is much less than your Ethernet connection. You could do it, you could use a good virgin fiber broadband would be compatible to what the information we push from our eyes to the brain. And that reduction in data, and yet still, to have such a wonderful experience of the world, and we see the important stuff, if you like, is something we have gradually to include in these sort of large sensors.